Hello everyone, I am Amulya, Assistant Professor in Electrical and Electronics Department, Sai Vidya Institute of Technology. In today's session, we are conducting an experiment on step response of a second order system. The aim of the experiment, so this experiment we are doing in a MATLAB. It is basically a simulation experiment. So in this experiment, we are going to simulate a typical second order system, and we are going to determine the step response and the evaluation of the time domain specification. So next, moving on to the second case, that is addition of the zeros to the left half of S plane. Next is addition of poles to the left half and also the right half of the S plane. So this is the aim of the experiment. So now coming to the time response. Time response is the response given by the system, which is the function of time to the applied excitation. So this is what we call it as time response of a control system. So this time response, it has two types. One is the steady state response, other one is the transient response. So we can write this as C of t will be equal to C into Ss plus Ct of t. So C of t is the time response, and it has been consisting of the steady state response and also the transient response. Transient response is nothing but, that is Ct of t, it is nothing but output variation during that time it takes to achieve its final value. So the variation in achieving the final value, so that is what we call it as transient response. So usually the transient response are oscillatory in nature. So next comes is the steady state response. So steady state response is, it is the part of the time response which remains after completion of the transient response. So that is what we call it as steady state response. So after all the disturbances are cleared in the system, then reaching to a stability condition or the stable condition, that is what we call it as steady state response. So these are the two types of time response it is. So now here in this experiment, first we are going to the simulation of the step response of a second order system. So this is the program for step response of a second order system. So what is the meaning of a second order system means? So this is the transfer function here. So it is the maximum value of S in the denominator. So observe here, this is the transfer function. So in the denominator, the maximum value of S is 2. So that is why we call this as second order system. So this is the equation. So this is the program for finding the step response of a second order system. So firstly, clear CLC. So these are the two common commands that we are using in a MATLAB. So clear and CLC. This is basically to erase the data which are there in the command window, current directory. So for that we are using clear and CLC. So then we are defining the omega n value, the natural frequency value as 5, and zeta value, this is the damping factor, that is 0.6. So numerator and denominator, it is nothing but our second order equation, second order transfer function it is. So this is the numerator and this is the denominator. Since there is no s square and s term, it is not there in the numerator. So in our the numerator program we have written n equals in the square bracket 0 0 omega n square. Then denominator will be equal to s square is nothing but 1, then give a space 2 into zeta into omega n. Again s is nothing but 1 only. Then giving a space omega n square. So this is the numerator and denominator. So next is time. Time will be equal to 0, then semicolon 0.1 semicolon 3. So what does it indicate means, in the graph it will be starting from 0 and ends at 3 with a time gap of 0.1 it is. So colon is basically used for defining the particular time it is or particular function. So that is why we need to use the colon here. So next is a system. So we need to find the step response of the system. Step response is basically the input we are giving it to the system in terms of steps. So system will be equal to, system is nothing but this whole second order system, that will be equal to transfer function of the numerator by denominator. So that is why we are representing numerator comma denominator. So comma indicates it is ratio, numerator by denominator. So then for this second order system, we need to apply the step input or the step. So the step of system comma t. So this is the first program of a step response. So one thing you need to observe, so for omega n equals to 5, we have put a semicolon here. Even for zeta also we have put a semicolon, and for t also. So what is the purpose of including a semicolon means, so these particular lines will be terminated in the command window. That means these lines it won't display in the command window. So now we'll see the program in the MATLAB. So this is the program we have typed in MATLAB in the M file. So first what you have to do, go to file. Once you open the MATLAB, go to file, go to new. In that you need to go to the M file. So once the M file is open, so then there you have to type this program. So this is your first program. So once the program is typed, then you need to use this particular icon for saving this program in the system. So you need to save this as, I'll just show an example here. So I already saved this program, go to save as. So you need to save this as any name you can give without any space, .m you have to save, because this is M file program it is. So .m you have to give, then save. So since it is already been saved, so now once the program is saved, so then you have to use this button. This is the run option. So here press this run button. So once the program is run means you are going to obtain this graph. But before seeing the graph, so now go to the command window. So this is the command window. So here you can see the result page. So this is our numerator and this is the denominator value and this is our final transfer function. So now observe the program here. So omega n value we have given it as 5 and zeta value we have given it as 0.6. So numerator is nothing but omega n square, nothing but 5 square it is. Similarly, denominator means it will be adding up of the zeta value and omega n value, and that will be displayed in the system. System is nothing but transfer function of numerator by denominator. And this step of system comma t is nothing but the graph what you have obtained here. So now observe the command window once again. So this is numerator, denominator, and this is the transfer function. So now observe the graph also. So this is the graph of the time domain specification. So in the time domain specification, there are different transient responses are there that you can able to see in this graph. So how to measure all these values means, so you need to right click, go to characteristics, then you have to select peak response. So peak response is basically we call it as TP. TP is nothing but time taken by the system to reach to the maximum peak value or the maximum disturbance in the system. So this is we call it as peak, TP. So here once you click the cursor over this button, so here there are different values will be displaying, that is the peak amplitude, overshoot at a time. So you need to note down the TP value, that is 0.8. So this is your TP value, 0.8 in seconds. Next similarly right click, again go to characteristics, now select the settling time. So settling time is nothing but TS. TS is time taken for the system to reach to the stability condition after coming out from all the transients or the disturbances. So now for the measurement of settling time, so again click on this particular dot so that the settling time will be 1.19 second it is. Again right click, go to characteristic, so then note down rise time, that is TR value. So TR is nothing but time taken by the system to reach to 90% of the peak value. Okay, so this is the 90%, this is the reference, and this is 90 for the given reference. So time taken by the system to reach to 90% of peak value, that is what we call it as a rise time. Again for measuring the rise time in second, so click here, the rise time will be 0.375 seconds. And the last characteristics that you can measure here is, that is steady state. So always the steady state will be equal to 1 it is. So this is all your practical values. So this is the time domain specification. So these are all the equations for calculation of the rise time, delay time, peak time, maximum peak overshoot. So as in the graph you have already seen the practical values of the rise time, delay time, peak time and the maximum peak overshoot that you have seen in the graph. So that is your practical values. Then the practical values should be compared with your theoretical values. Since in the first program they have already given the omega n value as a 5 and zeta value as 0.6. Now by taking the omega and zeta values, so you need to substitute in the omega d equation. First find out what is omega d, then calculate the theta value either by using this formula or by using this. So you will be getting 0.92 radian. Then it is in the terms of radian degree. Either you can substitute in the degree mode or in the radian. So better to substitute in the radian mode only in the calcium. Then the delay time will be 0.28 second, the rise time will be 0.55 second. Then the peak time is this value settling time and the maximum peak overshoot. Maximum peak overshoot means it is the percentage difference between the actual value with the desired value it is. So after calculation of this time domain specification, then we need to write this table. So this is like a comparison table of the theoretical value with the practical values. So here we need to write this particular column, that is 1, 2, 3, 4, 6. So totally 5 column you need to write. So here you have to compare the theoretical value with the practical values. So this is the theoretical value which we have calculated from the time domain specification, and the practical value, this is we have copied from the obtained graph. And similarly the peak time also, settling time also, the delay time and also the maximum peak overshoot. So this is your first program. So this is the second program, that is addition of zeros to the left half of S-plane. So here we are going to add zeros to our given transfer function. So this is the given transfer function. We are going to add the zeros. Zeros means it will be the numerator. Denominator will be the poles. So before adding up the zeros, so first we need to draw the graph for a step response. So this whole thing will be the program for drawing of the step response of a second order system, similar to the first program it is. Clear CLC omega n, here we are defining it as a 2, zeta will be equal to 0.6, numerator value same as it is in the given transfer function omega n square, denominator will be similar to this given transfer function, we are writing it in the denominator program, and the time delay. So the graph will be starting from 0 and it ends at 6 with a delay of 0.1 or with a time gap of 0.1 it is. So then system 1 will be equal to transfer function of numerator comma denominator, so that the given transfer function it will be displayed in this form. Transfer function will be equal to numerator comma denominator. So here it will going to substitute the omega n value and also the zeta value also will be substitute. Then we need to plot the step response for a given transfer function. So after that we need to put the comment as hold on. This is why, because we need to add the zeros to our second order system. So here some of the zeros values I am defining here. So these zero values we need to include in our given second order system transfer function. So before that I have calculated the transfer function here. So this is our transfer function omega n square of a second order system. So 0 is nothing but it is the numerator omega n square of s plus z. So now simplify the equation. Omega n square is multiplied as s plus z. Again, instead of writing s plus z in the numerator, I will write this as s by z plus 1. So now after writing in this way, so multiply omega n square, these two terms, that is we are going to obtain omega n square by z plus omega n square, divided by the denominator will be same as it is, because we added only the zeros in the numerator and the denominator will be same as it is. So you need to remember this transfer function, because this is our new transfer function after the addition of zeros. So this is the continuation of the program. So we added the new zeros here. So then there are totally 5 zeros are there, 0.5, 1, 5, 10 and infinity. So infinity is also one of the zeros. After 10 it will goes to infinity. So now consider for. So here we need to define a for loop here. So why? Because there are 5 zeros are there. All the 5 zeros also should need to be considered one after the other. So for that we are defining a iteration. I will be equal to 1:5. So first the 0.5 will be considered, then the new transfer function will be obtained. After that it will go for the next 0, that is 1. So likewise it will be continuous for all the 5 zeros. So then we need to again define the numerator. So this is the new numerator transfer function which we obtained after adding up of zeros. So now observe, this is the transfer function which we obtained after adding up of zeros in the denominator, in the numerator. The denominator will be same as it is. So observe here 0, because there is no s square term is there, then next to that omega n square divided by z is there. So we need to define this as, see in the program we have defined this as zv, even in the numerator also we have to define this as zv of I is nothing but iteration. So the program need to run for 5 times for all the 5 zeros, then with the space omega n square. Similarly we need to write the denominator will be same as it is. Then define a system, because this is our new transfer function. So here also the omega n and zeta values and 0 values need to be substituted. So totally 5 transfer functions we are going to obtain for this program. Then we need to plot a graph by considering the step input. Again we need to put a hold on comment and legend. So why is this legend comment is required? Means since we are getting a 5 zeros in our graph, so to differentiate or to identify what all the zeros values and what all its values, we need to put a legend comment, so that each graph will be represented with different colors. So this is the second program. So now we'll see the simulation part of the second program. So this is the second program, addition of zeros. I have typed in the MATLAB. So after once you type the program, save this by keeping .m, then run the program. So this is the graph for addition of zeros. So now we'll see first the MATLAB. So in the command window we can see totally 5 transfer function will be getting. So this is the transfer function before the addition of zeros. So this is the transfer function before the addition of zeros. After that we are defining the zeros here, totally 5 zeros are there. So since we are defined the for loop condition, so every zeros will be considered one after the other. So now for the first case, this is the transfer function by considering the 0 will be equal to 0.5. So substituting it in our transfer function, this is the numerator and this is the denominator, and we are going to get this as the transfer function for a 0.5. Similarly it will goes for the second 0, that is 1, so that we are going to obtain this transfer function. This is for the second 0. Likewise we are going to obtain 5 transfer function of the system. So we need to copy down all this transfer function for a different 0 values. So now observe the graph. So this is the graph for addition of zeros. So what you can observe from the graph is, due to the addition of zeros in the left half of the S-plane, it will going to speeds up the transients. See, as I told you, because of adding of the legend command, so we can see the different 0 values will be identified with different colors. So the red color indicates the 0 value will be 1, the green color indicates the 0 value will be 0.5. So likewise the remaining colors also of the graph also will be there. So now with this graph what we can understood means, due to the addition of zeros in the left half of the S-plane, it will go into speeds up the transients. That means these rising and falling of the graph will be takes place. These are all we call it as transients, basically oscillatory in nature it is. Smaller the value of z makes this effect more prominent. That means if the value of z is minimum means, so the effect of or the transients will be more in the system. See, observe this green color line, green graph. So here the value of z will be 0.5. That means that is why the peak or the transients will be more here. So now observe for the last one, z is equal to 10. So since the value of 0 is more, so there will be no transients are there, then the system will be reaching to its stability condition or to the stable condition. So addition of 0 in the left half of the S-plane makes the system faster and it makes more oscillatory. So this can be seen from the simulation. So this is the second program. This is the third program in the same experiment. This is addition of poles to the left half of S plane. So clear CLC, omega n, zeta, numerator, denominator, the time, system, step. So this is similar to the first program. So this whole program is for adding of the step response to a second order system. So after that we need to add the poles to the left half of S plane. Poles means we need to add in the denominator of the transfer function. So now for the adding up of the poles, these are all the 5 poles we are defined here. PV will be equal to 0.5, 1, 5, 30, infinity. So now for considering or running up of all the poles one after the other, we need to define a for loop condition. For will be equal for I equals 1 is to 5. I is basically a iteration. So one after the other poles it will be keeps on running. Then see in this we have skipped 2 statements here, that is instead of defining numerator and denominator separately, we have defined it in the system only. System will be equal to transfer function of, so this whole thing will be the numerator and the remaining this thing will be the denominator. So numerator comma denominator, so that is system. So then for this we need to plot a step response. So step of system comma t, again we need to put a command as hold on enter, and the legend is for displaying of or for differentiation of the poles here. So this is the third program. So now we'll see the result of this. Run the program. So this is the graph for adding up of poles here. So we'll observe the command window here. So even here also 5 transfer functions we are going to obtain. So this is the first transfer function before the addition of poles. After the addition of poles, these 5 poles, we are going to obtain 5 transfer function here. So this is the first, second. So likewise we have 5 transfer functions are there. So poles will be added to the denominator. So now observe the graph here. So in this graph what we can observe, with the addition of a poles to the transfer function, time to the first peak of the step response it will be increases and the percentage overshoot will be decreases. So the first peak, the step response of the system will be increases and the overshoot will be decreases. So we can increase the step response of the system by reducing its transient response by adding up of poles here. And in additional to that, the amount of oscillations that also can be reduced, that by using addition of poles to the left half of the system, so that the system will become more stable, less oscillated. Thank you.